Section 8.5, Rationalizing Numerators and Denominators of Radical Expressions. We will actually only rationalize denominators. A radical is in simplest form if the radical has been simplified as much as possible, meaning take anything out that can come out, and no radicals are left in the denominator. So if a radical is left in the denominator, we have to do something called rationalizing. And number 3, all possible sums, differences, products, and quotients have been found. So, to rationalize a denominator, that means we want to get rid of the radical in the denominator. We want to rewrite the expression so that the denominator only contains a rational number. So to rationalize, we're going to multiply the numerator and the denominator by a radical so that the radical in the denominator will be eliminated. For example, number 1, rationalize 1 over the square root of 2. Looking at the square root of 2, nothing can come out, but it's not in simplest form because the radical is left in the denominator. So we need to multiply top and bottom by some square root that's going to, in a sense, eliminate the square root in the denominator. So what I want you to do is think about powers and what are the nicest squares. So we have 2 squared, which is 4. So I would make a list, 2 squared, 3 squared, 4 squared, and so forth. And 2 squared is 4, and we know that 2 times 2 would give me a 4, so I need to multiply top and bottom by the square root of 2. So 1 times the square root of 2 is just square root of 2, and the square root of 2 times the square root of 2 is the square root of 4. And we know the square root of 4 is back to 2. So really we just want to multiply by a number that's going to have a nice square, so therefore we can take the square root. For number 2, we have the square root of 7 over 12. Well, let's separate those. We get the square root of 7 all over the square root of 12. There are a couple different ways to go from here. I'll show where we're going to simplify the square root of 12 first. If we simplify the square root of 12, we know 12 is 2 times 6, and 6 is 2 times 3. So a 2 is going to come out, and a 3 is going to be left. So now we need to get rid of the radical in the denominator. So we need to multiply top and bottom by some square root that's going to get rid of the square root of 3. Well, 3 squared is 9. We know that. So 3 times 3 is 9, so I'll multiply top and bottom by the square root of 3. Because they're both underneath the square root, we can multiply straight across. We get the square root of 21 all over, the 2's on the outside, and the square root of 3 times the square root of 3 is the square root of 9. Well, the square root of 9 is back to 3. So we end up with the square root of 21 all over 2 times 3. So we end up with the square root of 21 over 6. Now the other way is just to rationalize without simplifying first. So when we had the square root of 7 over the square root of 12, we need to ask ourselves, what is the first nice square that 12 can go into? Well, it's actually 36 because 6 squared is 36. And 12 can go into 36 3 times. So we can multiply top and bottom by the square root of 3. So on top, 7 times 3 is 21, so we get the square root of 21. And on bottom, 3 times 12 is 36, and we know the square root of 36 is 6. So we end up with the square root of 21 over 6. Same answer, just a different way to get there. So you can decide if you want to simplify first and then try and rationalize, or just go ahead and start rationalizing. So for number 3, we have 3 over the square root of 10x. Well, 10 is 2 times 5, so nothing's going to come out. So we need to multiply top and bottom by some square root that's going to have a nice square. Well, the first square that 10 can go into is 100. So we'll need to multiply top and bottom by 10. And we have x to the first power. Well, we need one more x, so when we multiply, we add powers, we're going to get an x squared. So we end up with 3 square root of 10x all over square root of 10 times 10 is 100, and x times x is x squared. The numerator cannot be simplified, but the denominator, we have the square root of 100, which is 10, and we take power divided by index, so 2 divided by 2 is 1, so x to the first comes out, and no x's are left underneath the radical. If the 3 and the 10 could be reduced, we should, but 3 and 10 cannot be reduced, so we're done with that problem. So number 4, 3 over the square root of 8. So again, we could simplify first. If we do so, we'll have 3 over 2 square root of 2, because 8 is 4 times 2, and the square root of 4 is 2. Then we could rationalize by multiplying top and bottom by some radical that's going to get rid of the 2 under the square root. Well, the first one that would be 4, so we need to multiply top and bottom by the square root of 2. So 3 times the square root of 2 is on top, and 2 times the square root of 2 times 2 is 4, so we get the square root of 4. The square root of 4 is 2, but we have a 2 on the outside, so we'll multiply those. So we end up with 3 square root of 2 all over 4. The other way to do it is not worry about simplifying. We just multiply top and bottom by some square root, and the first nice square that 8 can go into is 16. And so 16 divided by 2 is 8, so we can multiply top and bottom by the square root of 2. So we end up with 3 square root of 2 all over square root of 8 times the square root of 2 is the square root of 16, and the square root of 16 is back to 4, so we end up with the same answer. Number 5, the square root of 3m over 11n squared. Underneath the same radical, we look to see if we can reduce. Nothing can be simplified, so we do need to separate into each its own radical. So we get the square root of 3m over the square root of 11n squared. So looking at the square root of 3m, nothing can come out, but in the denominator, we have 11n squared. Well, we know what we can do with the n squared. So we take out an n and we're left with the square root of 11 still, and on top we get the square root of 3m. So the n came out and the square root of 11 is left. So the first number that 11 can go into that's a nice square is 121, so we need to multiply top and bottom by the square root of 11. Because they're both underneath the same index, we'll multiply 3m times 11 and we get 33m over n times the square root of 121. And the square root of 121 is 11, so we have the square root of 33m over 11n. Don't reduce the 33 and the 11. The 33 is under the radical, the 11 is not under a radical, so we are done. Looking at number 6, we have the cubed root of 6 over 5. 6 over 5 cannot be reduced, so we'll separate them into the cubed root of 6 all over the cubed root of 5. Now we have to think about cubed roots. So let's go ahead and think about what is 2 cubed. Well, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. We could go a little bit higher, but we'll start with those cubes. So the first number that 5 can go into that's a nice cube is 125. So we need to divide 125 by 5 and we get 25. So if we multiply top and bottom by the cubed root of 25, that should eliminate my cubed root. So on top we will definitely multiply those underneath the same radical. So it's the cubed root of 150 all over the cubed root of 5 times 25 is 125. And the cubed root of 125 is back to 5. We should do the factor tree on the cubed root of 150, but you'll see that there are no triplets, so therefore nothing can come out. So our final answer is a cubed root of 150 all over 5. Number 7, p over the cubed root of q. Well, q has a power of 1. So I need 3 underneath the cubed root for it to come out. So I need to multiply top and bottom by q squared, because when I multiply I add powers, so that's going to give me a q cubed. So on top we have p times the cubed root of q squared all over the cubed root of q times the cubed root of q squared. We'll add the powers, so we get the cubed root of q cubed. Now, that can be simplified. The top stays as is because nothing can come out of the radical. And on bottom, 3 divided by 3 is 1, so q to the first will come out. So number 8, 9 over the cubed root of 9a. Nothing can come out of the radical for now, so we need to think about what can I multiply top and bottom that's going to eliminate my radical. Well, the first cube that 9 can go into is 27. So 9 times 3 is 27. We have a to the first power again, so we need 2 more, so a squared, to make a cubed. And whatever we do to the bottom, we do the same thing to the top. So the 9 is going to stay on the outside, and we get the cubed root of 3a squared over, we'll multiply all that together, so 9 times 3 is 27. A to the first times a squared is a cubed. So then we'll take the cubed root in the denominator. The numerator doesn't change. The cubed root of 27 is 3. A cubed under the cubed root. An a can come out and no a's are left underneath. Now, can we reduce the 9 and the 3? And yes, we can, because it's multiplication. 9 times that cubed root and 3 times a. You're allowed to cancel when you have multiplication. So 3 is going to be on top times the cubed root of 3a squared all over a. We can't reduce the a's or anything because one's under radical and one's not. But numbers outside, because it's multiplication, are allowed to reduce. We have the fourth root of 5 over y cubed. So nothing can be simplified right now, so we'll break it up into fourth root of 5 all over the fourth root of y cubed. Well, we have y cubed. We need one more to make 4, so we'll multiply top and bottom by the fourth root of y and the fourth root of y. Because they're both underneath the same root, we'll go ahead and multiply underneath, so we get 5 times y on top under the fourth root. In the denominator, when we're multiplying, we add powers, so we end up with the fourth root of y to the fourth. So we'll take power divided by index in the denominator, and it gives me a y to the first. I don't need to put a 1 because it's understood to be there. So my answer is the fourth root of 5y all over y. Now, what if we had more than just one term in the denominator, like a binomial? So if the denominator of fraction contains a sum or a difference, you rationalize the denominator by multiplying by the conjugate. If you've never heard of the conjugate before, that just means the middle sign has to change. So if it was x minus 5, the conjugate would be x plus 5. So looking at number 10, we had 3 over the square root of 5 plus 2. Well, because it's a binomial, meaning two terms down the denominator, we have to multiply by the conjugate. This conjugate of square root of 5 plus 2 is the square root of 5 minus 2. So top and bottom gets multiplied by the square root of 5 minus 2. Well, 3 times the square root of 5, the 3 stays on the outside, and we get the square root of 5. 3 times negative 2 is negative 6. In the denominator, square root of 5 times the square root of 5 is the square root of 25. Outer is going to give me a negative 2 square root of 5. Inner is going to give me a positive 2 square root of 5. So those are going to cancel. And 2 times negative 2 is negative 4. Anytime you multiply by the conjugate, the outer and the inner are always going to cancel out. So on top I get 3 square root of 5 minus 6 over the square root of 25 is 5, and we get 5 minus 4, which is 1. It's understood to be there, so we don't need to put the 1 in the denominator. So my answer is 3 square root of 5 minus 6. Number 11. 4 over 3 minus the square root of 5. Again, it's a binomial, so we're going to need to multiply by the conjugate. And the conjugate of 3 minus the square root of 5 is 3 plus the square root of 5. So we'll distribute the 4 on top. 4 times 3 is 12. And 4 times the square root of 5, the 4 stays on the outside, and the square root of 5 stays underneath. Remember, we're really multiplying the 4 times the 1 in front of the radical. Well, 3 times 3 is 9. I'm not going to show outer and inner because with conjugates they always cancel. And the last, I get minus square root of 5 times the square root of 5 is the square root of 25. So we end up with 12 plus 4 square root of 5 all over, well, the square root of 25 is just 5, so 9 minus 5 is 4. Separate those into each its own fraction, and then you can reduce. 12 over 4 plus 4 square root of 5 over 4. So 12 over 4 is 3, and 4 divided by 4 is 1, so we just end up with the square root of 5. So final answer is 3 plus the square root of 5. Number 12. We have 4 square root of x all over the square root of x plus 1. Again, we have a binomial in the denominator, so we need to multiply by the conjugate. The conjugate of the square root of x plus 1 is the square root of x minus 1. So we'll multiply top and bottom by the square root of x minus 1. When we distribute, the 4 stays on the outside, and the square root of x times the square root of x is the square root of x squared. 4 times negative 1 is negative 4, and then square root of x. In the denominator, square root of x times the square root of x is the square root of x squared. Again, I'm not going to show outer and inner because they just cancel each other out. And 1 times negative 1 is minus 1. So now let's go ahead and simplify the numerator. Well, square root of x squared is just x, so we end up with 4x minus 4 square root of x all over the square root of x squared is just x, and we get minus 1. Nothing can cancel. You could try and factor out a 4 from the top, but because we have subtraction on top and a subtraction on bottom, we have glue in a sense. So if we were going to cancel anything, the whole factor would have to cancel. And whole factors cannot cancel. So our final answer is, if you want to factor out the 4, you get 4 parentheses x minus the square root of x all over x minus 1. You don't need the parentheses, they're understood to be there in the denominator, but if you factor out the 4, you definitely would need the parentheses in the numerator.